Hi, welcome back to the quantum chemistry part 2. Here we talk about Bohr model and the hydrogen atom and this atomic spectrum. Um, Very common, where day-to-day application for atomic spectrum is fireworks. And then, if you see the building, that's another example of emission spectrum. What is that emission spectrum? The emission spectrum also it's atomic spectra. Atomic spectra is when you have the element, you put the element and you provide energy to this element, and then this element has the atoms, and atom has the electrons in a certain energy level. Remember, I told you that electrons in an orbitals. These orbitals take an energy and go to upper energy states, and then when they come to the lower energy states, the upper energy states are unstable, and then they come to lower energy states, they release the energy. That release energy falls into the visible light. We can see it in colors. So this is the thing I'm talking about. So this is the hydrogen spectrum. Hydrogen, like any atom, so you have electrons. So when you provide energy, this electron absorb this energy and go to the higher energy states. It can go here, it can go there. So when it goes to high energy states, very unstable. So then it slowly release this energy and come to the lower energy states. This energy that releasing is fall in the visible light. We can see it in colors. So that's the basic principle of the atomic spectrum. So here in this atomic spectrum, you see how do you calculate the energy that releasing between these two transition. For that, we have an equation. How do you calculate the energy between the transition of an one atom? It is, you can calculate that using, you don't have to memorize the equation. You can write, like I let you bring the formula equation sheet or formula sheet. You can write it, but I want you to understand the equation. So 1 over lambda, 1, just 1, and lambda is wavelength. R is a new number that coming to the picture. It's Rydberg constant. It is R. It is a long constant. 1 over N1 squared, 1 over N2 squared. So what is this N1 and N2? N1 and N2 are whole numbers. They are the where the orbitals that electrons can locate it. N2 is bigger. That means, so if I draw here, so this is my atom, and one it goes like that, goes like that, goes like that, and then think about I erase it like this. Okay, I erase it. So I have this, so it's easiest for you to understand. So I'm drawing here. Think about I erase here too. So this is what I draw, and then I have one. So this is the transition. So I'm asking you find the transition for this energy. So I know N equals 1, N equals 2. So here the N2 is bigger. So the bigger number is N2. So this is N2. Okay. So and then so you can always get the energy. So let's do a calculation without doing it. So let's look at this question. So they came up with this equation. So this equation, its equation is given for 1 over lambda and the Rydberg constant and everything. But another equation, E equals H mu. Remember? E equals H mu. And then mu equals C over lambda, right? Remember the C equals, very first equation we learned, lambda and mu. So then you can apply, instead of mu, E equals H C over lambda. And then, I know it's not clear, let me write it again. E equals H C over lambda. And then using this equation, they by rearranging, they came up with this one: E equals its mu equals negative 2 point. That's all the rearrangement. That's all the mathematical part. Mainly in the exam and the homework, I try to stick with that one, but I want to show you where it originally coming from. So then it's the basic equation, main equation we are learning today, the important one. E H mu equals negative 2.18 into 10 to the power negative 18, 1 over n final squared minus 1 over n initial squared. So here final means if it is absorption, that means absorb energy, final always go to the bigger number, right? But if it is a relaxation, that means relaxation means you release the energy, 2 to 1. So 1 would be the final, initial would be 1. So final would be 1 and final would be 1 squared, initial should be 2 squared. So we'll do a calculation, then it's easy for you. So let me update. So you can always, so when you know this equation, you can rearrange it and you can find the, sometimes, mostly this equation, they say, okay, the electron move from 3 to 4, find the energy associated with the transition. So then you need to know electron move from 3 to 4, 4 should be final, this should be 4, this should be 3, and then find the energy. And then when you know energy, you can find because using E equals H mu, you can find frequency, and then anything you can, most of the information you can get it. So this is the emission spectrum, and then so there are series in the line spectrum. We call Lyman series, Balmer series, Paschen bracket. These are the like series. There's a lot of scientists identify. We mainly see the Balmer series. Balmer series means, like always when the electron excite, it comes to the sex. So this is like N1. So this is our nucleus. Orbital 1, orbital 2, 3, 4, like that. It goes up. And initial, so these are all relaxation, losing energy. So in the high energy states, come to the second um, cell, second orbital. Then we see Balmer series. Why Balmer series is important? It is where we can see all the atomic spectrum. If you want to see, it should come to the Balmer series. Lyman, it's come to the very first one. We don't see it. That's okay. Let's look at the calculation. That's important. Calculate the wavelength in nanometers of a photon emitted when an electron transition from N4 to N2 state in hydrogen atom. So I have to calculate the wavelength. So so the setup 1 over lambda equals 2.18 into 10 to the power negative 18, like that. So H, and then once you find this equation, once you apply to this 1 over lambda equation, so we have this equation I'm talking about, equals H mu. So you see the rearrangement, right? So this is the 1 over lambda, delta E equals H mu, this is about this equation. So where the lambda comes to the mu. So mu you can represent using 1 over lambda. So because the equation is H, let me write it here so it's better. So this one. So E equals H mu 2. So now how do you substitute with lambda? So E, in fact, like E, it should be, E is there. So let's see. mm, mu, okay? Mu equals c over lambda, okay? So instead of h mu, you write h c over lambda equals negative 2.18 into 10 to the power negative 18, 1 and final, like that part, okay? So now you take 1 over, you keep 1 over lambda here, negative 2.18 10 to the power negative 18. I think this negative sign is missing here. There should be a negative sign, okay? There should be a negative sign. Negative 2.18 10 to the power 18 divided by HC. So this is the equation we're using for this particular calculation. So that's what I'm showing you. I think this should be here, it should be negative. Okay, but it's we usually you take the arbitrary value. Most of the time we take the arbitrary value, so it doesn't matter because it's a lambda is doesn't there's no negative for the lambda. That's why they didn't pay attention for the sign. So 1 over lambda, so you may wonder where the negative sign, because lambda is an arbitrary value. It should be positive for sure. There shouldn't be negative lambdas. So 1 over lambda equals 2.18 into 10 to the power 18 divide h is the Planck constant, and then it's given here the c is the 3.8 into 10 to the power negative 7, and it's the move from final state is 2 1 over 2 squared minus 1 over 4 squared. So you do the math part and then you get the lambda 1 over lambda in meters per square, but you want to convert into meters, so it's 1 over lambda and then you convert into meters. So basically you get the answer 1 over lambda equals 2.055 into 10 to the power negative 6. So you want to get the lambda equals 1 divided by 2.055 into 10 to the power negative 6. So when you do it, you get the answer lambda equals 4.87 into 10 to the power negative 7. And then you get the answer in the meters. In order to convert nanometers, you multiply by 10 to the power negative 9, and this is what the answer you are getting here. Okay, so this is how you use this equation the Rydberg equation to find the energy between two transitions. So I'm going to stop this part from here and I'll come back to the quantum numbers.